this module, we will look at charge sharing and energy storage on capacitors. Consider the circuit shown on screen. It consists of a 12-volt DC battery, two capacitors C1 and C2, and two switches S1 and S2. The capacitors are initially discharged, and as a result, the voltage on both of them is 0 at time t is equal to 0. The switches S1 and S2 are normally off, however they come on at certain time instance. S1 is on during 1 to 2 seconds and S2 is on during 3 to 4 seconds. Consider now what happens in the circuit during the time interval from 0 to 1 second. During this time interval, both switches are open and none of the elements are connected to each other. As a result, the capacitor voltages remain at 0 for the entire time interval. Since the capacitor voltages are 0, the charge is also 0. And since, once again, the voltages are 0, energy stored is also 0. Consider now what happens during the time interval from 1 second to 2 seconds. During this time interval, the voltage source is connected to the capacitor C1, and the circuit looks like the following. And capacitor C2 is once again not connected to anything in the circuit. Now, since the capacitor C1 is connected to the battery, it will get charged up to 12 volts and will remain at 12 volts for the entire time interval. So VC1 during this time interval will be 12 volts and VC2 will remain at 0 volts. Consider next the charge and energy stored on both the capacitors. The charge on capacitor C1 will be simply C1 times VC1 of t, which will be equal to 5 millifarads multiplied by 12 volts is equal to 60 millicoulombs. The charge on C2 will be 0 since the voltage on it is 0. The energy stored on C1, let's call it UC1, will be equal to half C1 V squared, which will be equal to half into 5 millifarads multiplied by the voltage squared, which will be equal to 0.36 joules. Also consider the energy supplied by the 12-volt battery. Now the charge on C1 is given by QC1, 60 millicoulombs, and all of this charge has come from the battery such that the top plate of the capacitor is positively charged and the bottom plate is negatively charged. Energy supplied by the battery is going to be equal to charge times voltage, which will be 60 millicoulombs multiplied by voltage will be equal to 0.72 joules. Notice that the energy provided by the 12-volt battery is double the energy stored on the capacitor, which leads to the first surprising thing about this circuit, that half the energy, or 0.36 joules, is lost. This energy is not disappeared, it has simply been lost as radiation, and we will talk more about this later on in this course. However, the most important thing to realize is that the 12-volt battery supplies 0.72 joules, however only 0.36 joules is stored on the capacitor C1. Consider next what happens during the time interval from 2 to 3 seconds. During this time interval, both switches are open and all the elements are disconnected from each other. As a result, the capacitor voltages remain fixed at what they were just prior to 2 seconds, which is VC1 remains at 12 volts and VC2 remains at 0 volts. Since the voltages on the capacitors does not change during this time interval, then everything, the voltage, the charge, and energy remain constant during this time interval. Consider what happens during the time interval from 3 to 4 seconds. During this time interval, the two capacitors are connected to each other and the circuit looks like the following. The voltage source is disconnected from the two capacitors. And since C1 was positively charged on the top plate, negatively charged on the bottom plate, there will be charge sharing between the two capacitors, so that some of the positive charge will move from the top plate of C1 to the top plate of C2, and similarly a negative charge will move from the bottom plate of C1 to the bottom plate of C2. This charge will continue to move till the two voltages on the capacitors become equal because they are connected in parallel. So VC1 will be equal to VC2 during this time interval. To be able to calculate the final voltages on the two capacitors, we know charge conservation must hold so that the final charge must be equal to the initial charge on the two capacitors taken together. The final charge will be C1 VC1 of t plus C2 VC2 of t, which must be equal to the initial charge, which was 60 millicoulombs on C1 and 0 millicoulombs on C2. So we can solve this equation for VC1 of t, which is also equal to VC2 of t, and the solution will give us that VC1 of t will be equal to 60 millicoulombs divided by the sum of the two capacitors, which will be 5 into 10 to the minus 3 plus 3 into 10 to the minus 3, which will give us the final voltage as 7.5 volts, which is also equal to VC2 of t. If we look at the energy stored on each of the capacitors, we can calculate the energy stored on capacitor C1 is equal to half C1 V squared, which will be and if we calculate that value, this will turn out to be 0.14 joules. Similarly, the energy stored on capacitor C2 will be half C2 V squared, and this value, if you calculate, will turn out to be which will be equal to 0.0844 joules. Next, consider the total energy stored on both the capacitors, which will give us .2244 joules. Notice that this energy is less than the energy stored on C1 just before it was connected to C2. If you recall, the energy stored on C1 at t is equal to 2 seconds was equal to 0.36 joules. Hence, once again, in charging up C2, we have lost some electrical energy, and we will discuss this loss of energy later on in this course.